So I'm going to talk about opening the box, diagnosing operating system task scheduler behavior on highly multi-core machines. So the goal of this talk is to understand the impact of the operating system on application performance. So in this, we're going to focus on the Linux kernel, and we're going to focus on the task scheduler. The goal is to diagnose performance regressions, and we're going to be focusing on large multi-core machines. Maybe I should have introduced myself first. I'm a researcher from Inria in Paris. I work on operating systems and all kinds of things, performance, maintenance, other things. I don't know if anyone of you is familiar with the tool Coccinelle, but I also work on Coccinelle. If you have any questions about Coccinelle, just get in touch. So the task scheduler Linux kernel. So what's the goal of a task scheduler? The goal of a task scheduler is to place tasks on cores when they are forked, when they're created, when they wake up, and when there is load balancing. It selects the task on the core to run when the core becomes idle, and what we're concerned with are two files in the Linux kernel source code, which are basically kernel sched core.c and fair.c. So the question is, how can a task scheduler impact application performance? To place and select tasks, the scheduler has to make decisions. Actually, in the case of a general purpose operating system like Linux kernel, the scheduler has absolutely no idea what the tasks are going to do in the future. On the other hand, knowing what they're going to do in the future is absolutely critical for making correct decisions. So it's kind of a difficult situation. So basically what it does is rely on some past information, but this is kind of problematic because poor decisions can slow tasks down, sometimes in the long term, because often if you make a bad placement, it takes a long time. It can take a long time to recover from that. So we're going to start by looking at several issues. One of them is called work conservation. So assume we have a little tiny machine like this, 4 cores, and we have a task that wakes up, T1. All the cores are empty at the moment, so the question is, where should we put it? And actually, it doesn't really matter where we put it. Anywhere is perhaps fine. We'll put it on core 0. And now we have another task that wakes up, which is going to be task 2. And then we can ask, where should we put it? Maybe we would like to put it on core 1 or core 2 or core 3, because nothing else is running there. On the other hand, if we put it on core 0, that would be a bad choice, because then we have 2 tasks sitting on 1 core. The core can only do one thing at a time. And we have this idea of work conservation. We have an overload in one situation, and we have idle cores in another situation. So we could put it, for example, on T2. Another issue that faces scheduling is the issue of locality. So now suppose we have a 2-socket machine. So we have 2 separate Newman nodes. We have like these cores that are a bit separated from each other. And now again, we have our task T1 on core 0. And we have another task T2, which has woken up, and where are we going to place it? So maybe we could put it on core 1. Core 1 is idle. And if T2 communicates a lot, for example, with T1, that might be a good place for it. It's at the same, on the same socket. Or if maybe T2 previously ran on core 1, and so it has allocated some memory there, and then it will be easy for it to access that memory. On the other hand, if we put it on core 2 or core 3, if it's accessing memory on core 1, then that might cause a slowdown. On the other hand, core 0 and core 1 might be sharing some physical resources, and core 2 and core 3 might be sharing some physical resources. So if actually T1 and T2 have nothing to do with each other, it might be better to separate them. So this is an example of how the scheduler really has no idea what's going on, but has to make some decision that's going to have an impact on the performance, and it's the performance of the execution of the application in the near future. So it's not the cost of scheduling itself, it's the cost of putting things in a bad situation so that they behave in a bad way. So basically, as I've tried to emphasize, the task scheduler can have a large impact on application performance. So there's a need to understand its behavior quickly and completely. Okay, so you can run your application 45 times. You can see how much time it takes. Sometimes it gets faster, sometimes it gets slower, but that doesn't give you very much information about what's really going on inside the operating system. But unfortunately, the task scheduler is buried very deep inside the operating system, so it's not completely obvious how you get the information out. So that's kind of the topic of this talk, which is how can you get the information out of the scheduler and understand it in a way that you can help debug some kind of scheduling problems. So how can we understand what it's doing? So fortunately, there is some help. There's a tool which is called trace command, and trace command will collect traces of scheduling and actually other kinds of events that happen in the operating system, but we're just focusing on scheduling. So it's quite simple to use. So you just run it as, I think you have to be root at least, but you can run it as a user level application. Trace command record, and then you give it the events that you're interested in, and then you give it some command, and this command can have arguments, so just run your application in a natural way. And then afterwards you get a file which is going to be called trace.dat, and then you can use the report command for trace command, and then you can get out a text file that will show you all the events that have happened at the scheduling level. So these events are, it's very low level. So this, I've shown just 4 lines here to give you a feel for what it looks like. But actually you'll get out, depending on the activity of your application, maybe even gigabytes worth of data. So you can see on the far left, you can see what task caused the event, then what core the event happens on, then what time the event happens, the event itself, and then some other information. So the first we have a wake up. Some task wants to wake up on a certain core. It wants to wake up on core 62. Then we have a sched switch. So you can see swapper is the old task, so that's just the idle task. And then compiler 3 is the new task, so that's the context switch that's happening. Then we have another sched switch. Compiler 3 is done, it's going back to swapper. And then we have waking, maybe some interrupt has occurred and some task wants to wake up, and we have to decide where to put it. So this is just a very small example. The things are ordered chronologically. You can see these are events that are happening on different cores and involve different tasks. So it can be hard to figure out, to kind of trace through and see what the tasks that you're interested in are actually doing. Fortunately, there's some help for that. There's a tool which is called Kernel Shark. And Kernel Shark gives you a graphical front end for the data of trace commands. So you can see what's happening on each CPU. It also has an option where you can see what's happening on each PID. It has little colors in the CPU mode, it has little colors to show the different PIDs. It shows a unit of time. You can zoom in and out. You can see the events at the bottom of the screen. So it's a fairly comprehensive view. It's quite easy to use. But unfortunately, it's kind of spacious. And so if you're thinking about a large machine with maybe 128 cores, it doesn't really fit nicely on your laptop screen or maybe even on a larger screen. So at least I have found in practice that when you have a big machine and it has an application that's using most of the cores, to get some kind of feeling for what's going wrong, where the problems are, and so on, you somehow need a bigger overview. You need to be able to see everything that's going on at the same time. So we tried to make some tools that can show all the activity on all the cores at once. They can scale to multiple gigabytes of trace data. And the thing that I have found convenient, maybe it's a personal preference, is to have files that can be saved and shared and so on, so to have PDFs. But we have recently we've developed a new interface which is using the implot library, and then you can have a graphical only image and you can zoom in and zoom out interactively. But then your only choice is to make screenshots. There's no PDF that you can use in the future. So I'm going to talk about 4 different tools. We have DAT2Graph, which is it's just showing you, it's kind of like Kernel Shark. You have your CPUs, you can see what's going on each CPU. It's kind of a horizontal bar graph, so you see lines going back and forth. We have running waiting. So running waiting is more of an overview. It shows you a green line with with the number of tasks that are running, and a red line with the number of tasks that are runnable. So that's very limited information, but it's very useful because you can see exactly where there's some kind of overloads and thus bottlenecks and thus sources of poor performance. Going in a much more detailed aspect, we have Stepper. Stepper shows every single core on the machine and what tasks are running and waiting on that core and what event is happening. So you can step forward and to a limited extent backwards and see exactly what's going on. And finally, we have Events. Events is sort of like Datograph, but it can show other events, not just scheduling events. So we'll see all of these things later. All of these are publicly available. We'll have the URL at the end of the talk. Here's an example we're interested in. This is a quite simple, or in principle, a simple example, but it's turned out to be very complicated. It's from the NAS benchmark suite. These are kind of kernels of scientific applications. This benchmark does something. It doesn't really matter what it does. What is important is that the benchmark has n tasks, and we're going to put them on n cores. And so in principle, this should be completely uninteresting from a scheduling point of view. We just put all our tasks on those cores. They should just sit there and run as fast as possible towards the end of the execution. So we can look at the performance on, I call it Linux 6.11++. So it's 6.11 plus a few patches that I've added at the end, which are kind of have an impact on scheduling and are relevant to what we're doing here. And so I've run it 20 times, and I've plotted the running time from the fastest one on the left to the slowest one on the right. And you can see mostly it's fairly stable, but there's kind of an upward trend on the right-hand side. So we're interested in why do we have upward trend? We have application that should be completely uniform, should completely run the same way all the time. Why doesn't it just stay basically at the same runtime value? And just for comparison, I mean, this is a scientific application. Traditionally, people just pin scientific applications and don't let the scheduler intervene at all. So I've just compared the performance, and then you can see when you pin it in kind of the optimal way, it stays at an even lower value. But with the scheduler, we can get close to that. On the other hand, you see on the right-hand side, we have that substantial overhead. So this difference perhaps suggests that the issue is related to memory locality. Because if we let the threads circulate among the different sockets, they don't get as good performance as they get if we just force them to stay in the same place where they have allocated their memory and can keep working on it. So now we can look at our tools to try to get a feel for what's going on. This is a fast run. We have the cores numbers on the left-hand side, so it goes from 0 to 64. This is a 2-socket machine with 32 cores, basically 32 hardware threads on each socket. And on the x-axis, we have the time. And you can see this run takes about 8.5 seconds. So we have another run here. This one's a bit slower. This one's taking a bit over 9.5 seconds. And then we have our slowest run, which is taking almost 11 seconds. Okay, so the goal is to look at these graphs and try to see what the problem is and try to get some idea of in what direction we should look. So I'm not sure if you can see the graphs well enough from where you're sitting, but if you study these graphs, you can see that the slower runs, the slower one and the slow run, both have some gaps. So there's a gap here. There's a big gap here near the bottom of the screen. There's a smaller gap up here. These are perhaps a bit suspicious. And if we look at the very slow run, we have some of these sort of little gaps or moderate-sized gaps in the middle, but then there's a huge gap over here on the right-hand side. Basically, the last 4 seconds, we are using only 31 cores on one socket. There are only 31 threads running there, and there are 32 cores on the other socket because that's how many there are, but there's actually 33 threads running there. So that seems like a problem. So basically, in general, what's the issue with gaps? If you have a gap in your graph, then there's two possibilities. One is there's actually nothing to do, and so that has no impact on performance. Another possibility, though, is that some cores are overloaded and that some cores are not doing anything at all. So we have a work conservation issue. So that will cause a potential slowdown. In the particular case of the BT, application, all of these threads are regularly synchronizing. And so if one thread slows down, or actually two threads will be slowing down, because if you have two threads on a single core, they will be alternating between each other, and they will each go half speed. We have those two threads that are slowing down, that will slow down everyone else because they will get to their synchronization point and no one will be able to proceed until the slowest one gets there. So it has a big impact on the overall impact of performance of the application. So to look into this a bit more, we have the running waiting tool that I mentioned previously. And so we can see, where are these overloads? How big are they? What's going on? So this is the fast run. So you can see the green line, as I mentioned before, the green line are the running ones. So we see we have 64, basically most of the time we have 64 threads running all the time, which is good. There's a few places here where a bunch of threads goes to sleep, and so then we have fewer cores that are running. We also have lots of little red things over here, so that means that there's more runnable threads than there are cores on the machine. Those are necessarily waiting in some wait queue because there's more of them, there's no place for them to run. But there's kind of a optical illusion that you can have, which is the plotting tool has a certain minimum width for the lines. And so when you see a line that's a thin line, you don't really know if it's a thin line, just how thin it is. So there are many overloads, but they may be very brief. Maybe there's some kind of daemons that start up for just a few microseconds. So we have another option which is called forked, and that's only going to show us the threads that we forked. Those are the ones that we're really interested in. We want to be sure that they are running all of the time or most of the time. And so things look much better here in our fast run. There's one little tiny red place here, but this is perhaps some other thread, not actually the application. Mostly the application is using the entire machine most of the time, and we get good performance as we expect. On the other hand, on the slow run, then we can start to see the problem. When we had those gaps, here we have the situation where the green line is below the number of cores available, so we're not using all the cores on the machine. On the other hand, there's a red line which is at the number of cores, and so that means that there is a runnable task somewhere and it's not running. And then you can see here at the end region, we have that situation for quite a long time. So it might look like a small gap between the number of running threads, which is 63, and the number of cores on the machine, but it actually has a quite strong performance impact. So then we can go back to our data graph and try to see what is actually going on. Basically what we're going to do is we're going to look at this place here in detail to see what's going on the machine at that point, to see what is causing the problem. So I don't know if you can see it very well. So what I've done is I've zoomed in to a certain region. I've used this option, which is color by command. So now the previous lines were colored by the PID, and now they're colored by the command name. So we can see blue most of the places because that's our application. But maybe you can see, I don't know, in these places that I've circled here, there's a little tiny green line. And the little tiny green line is the migration task. And the migration task is something that's used in load balancing. Basically, the point is that when a task is running, you cannot just take it and move it off to some other core. So if you want to migrate for load balancing, if you want to migrate a running task, first you send in a migration task that's high priority that will preempt the task that you want to migrate. Then you can pick it up and move it over to where you want it to go. So this is a sign that some kind of load balancing is about to happen. But we can wonder, why do we need load balancing? Because we have n threads on n cores, we should never be overloaded for any substantial amount of time, so we should never have any need to balance the load. So here, now we can look at stepper, we can see exactly what instructions are happening, what events are happening at each particular point. Here you see one socket over here, the even numbered cores, another socket over here, the odd numbered cores. You can see at the start of this region, all the threads are nicely placed on their individual cores. Everything is perfectly good, how we expect the application to run. And then if we look down here at the event, then we can see it's called sched move NUMA. So this is nothing to do with CPU load balancing. This is balancing that is supposed to be addressing memory issues. So there's a feeling that some thread, we can see which one it is here, PID number 14078, is actually accessing a lot of memory on the other socket, and so there's the idea that we would like to move it over to the other socket in the thought that it will perform better over there. So there's actually two kinds of NUMA balancing that are possible. One is where you just switch two threads, one from one socket, one from the other, so that doesn't have any real unfortunate scheduling impact, but that's not the one we're doing here. We're doing NUMA move, which is where you take a task on one socket and just drop it on the other socket and let whatever happens happen. So that's what we're doing, and actually we do it twice. There are two threads that we feel like we should be moving. So here you can see the migration threads waking up on these two cores. Then the migration threads are going to preempt those two threads. Then those two threads will get sent off to the other socket. And then the migration threads are done with their work, and so they will go to sleep. And so now we're in a work conservation situation where we have clearly some idle cores over here, and we have these two unfortunate threads over here that are waiting for the chance to run behind some other threads. They're competing with themselves, other threads of their own application. So I said these things already. The NUMA balancing is trying to address locality, but actually we're trading off better locality for less CPU access. And that less CPU access is going to persist over time. And so that has quite a detrimental effect on performance. So the question then is why we have an overload, which is a quite undesirable thing. Why does that not get corrected? So to look at that, we need to look a little bit at the implementation Linux kernel, the load balancing functionality. So load balancing is something that is run by a core, and then the core wants to look around on the rest of the machine and see if there's something it can steal. So the load balancing function starts out with three tests. Should we balance? That's kind of a basic test. Are we allowed to be the one who's stealing things? And then if it's allowed to steal, then it should find another group of cores that it could steal from, and then a single run queue in that group that is the best one to steal from. So it's a hierarchical system that has to do with the fact that it's a big machine for scalability and so on. So basically we have these three tests, and if any of them fails, then the whole process gives up. If we are able to steal, then we go around and actually look and see what's on that core and see if there's a task that we can steal. If we can, that's great. We have resolved our load balance situation. And if not, then there's another kind of load balancing, which is called active balancing, that has kind of lower criteria for whether you can steal or not. In particular, this box that says able to steal will never steal a running task. Active balancing might steal a running task, sort of in desperation, in hopes of clearing things up so that other kinds of load balancing can clear things up later. So the question is, where do we get off track in this process? So for this, previously we were using just the basic trace command. This is using the trace points provided by ftrace. But now we have some specific things we want to test, and so we need to do something more. We want to add our own events. There's a operation you can add in the kernel, which is called trace printk. And this is just like normal printk or normal printf. There were talks yesterday about BPF. Maybe you can do this with BPF. I've never really looked into it, but if you're expert in BPF, maybe you would know how to do that. And then we have another tool which is called events, which is going to show where these new events are happening and their relationship to other things happening on the machine. So here we've put in our trace printks at the inside those various tests to see which of them fail, to try to understand why they're failing. So if you look over here, we have 40 attempts to load balance. And in 33 of them, we have failed to find a run queue that we can steal from. So there's some other reasons here that we'll look into more later. But we'll start with this one. This find source run queue fails the most often. So basically what happens is that attempt to find a run queue to steal from has the impression that the load is already balanced on the machine, and so load balancing is not worthwhile. And so actually the load balancing heuristics are very complex. The first thing it does is to try to categorize the different try to categorize the general load balancing situation. And one of the categories is called migrate util, and one of them is called migrate task. So migrate util has kind of more strict constraints on whether you're allowed to load balance. Migrate task is just counting the number of tasks. That's quite suitable for what we have, because our problem is that we have 31 tasks on one socket and 33 on the other. So we just kind of force it to change the kernel to force it to use migrate task instead of using migrate util. And then we are, our core here on that underloaded socket, it's idle. It's looking what's going on that overloaded socket. It has been given the right to steal. It's looking for a queue that it can steal from. But unfortunately, it doesn't find any, because it looks at, now it's looking at every single queue in detail, and it sees that each one of them has already, because of the NUMA balancing round, they've all decided they prefer to be on this other socket. So the normal load balancing box fails, and we need to move on to active balancing. So now basically what we've done, this is the same kind of graph I showed before. Again, we're seeing why things fail at what point. And now basically we have a bit fewer attempts. This is a different run, so it's a bit different situation. We have a bit fewer attempts at load balancing, but now we've basically switched all of our find run queue failures to need active balance failures. So we've gotten to this desperation part of the load balancing, but that one is going to be failing over and over again as well. So the main issue, so this is the basic test expression that's going to decide whether we're going to get to do active balancing or not. Remember, active balancing can steal a running task. That's kind of a violent operation. And so there's an effort to not do that unless it's absolutely necessary. So that's the reason for this threshold. So we have migrate task. That's one of the constraints, but fortunately we already switched to migrate task. And then the other constraint is this one. Here we have a counter, which is called number of balance failed. So it's like if we fail, we want to fail a few times before we switch to this option. And then we have this other threshold here. This value is always 2. So we have to have, our counter has to reach a value that's greater than 4. So here is a graph that I have kind of made by hand, and it's going to show you the actual counter values that we achieve. So you can see here we have, here's a 0 and a 1. They're kind of right on top of each other. It's just a little bit hard to see. 0, 1, 2, 3. But then some kind of other failure happens. Find source group, either finding the busiest group or finding the busiest run queue, that fails. So then the load balancing thinks the machine is completely balanced. It sets all the counters back to 0. And then we have another, the whole thing fails again. Now we go up to 1. Now we get another one of these. This time it's, we couldn't find the busiest group. We go back down to 0. 1, 2, 3, 4. We're almost there. All we need to do is get to 5, but we don't. We have, again, finding the busiest group fails. And then, so it just goes on over and over again after that. So you can see that here in this case, this takes 1.5 seconds, but in our original run, it went for on and on for like 4 seconds, which is quite a huge amount of time. So to complete this, then we need to think about what do these functions do. I'm not going to go into a great deal of detail about them, but basically for finding the running queue, there is some kind of effort to categorize the socket according to whether it has any tasks that have expressed a preference for a particular socket. So if there are some tasks that have no preference, then the load balancing puts itself in a certain state, and it only tries to steal from those cores that have a task with no preference. Otherwise, it will just consider everything. But the problem is that it's we call a window of visibility problem. You analyze the situation first, and then a little bit of time goes by, and during that time, you might have found some tasks that were not particularly attached to a particular socket and thus stealable, but those tasks might have stopped running completely. And so then when we actually try to select a busy run queue, maybe those tasks have disappeared. And so all the remaining tasks are attached to a particular socket and we can't steal them, and so we say nothing to do and we give up. So that's for finding a busy run queue. We get a similar situation if we try, sometimes when we try to find a busy group. Remember, we have two groups. One has our local group, the one that's trying to steal, has 31 threads normally. The other one has 33 threads. But it can happen that during the time when we are counting the threads in the two sockets, the number of threads can change. So one reason the number of threads can change is there's some kind of useless, because on this socket that is overloaded, remember all of these cores can do their own thing at the same time, and so they can be doing some other load balancing where they just have the overloaded thread which is just bouncing around the socket. And so during the time that thread is being stolen, actually there are only 32 threads on the socket. So now we have one with 31 and one with 32, and then we don't see any reason to load balance. It's a very short period of time, but it can happen. And another issue is that sometimes some random daemons will conveniently use this idle core, and then it will seem like there are 32 threads on that core, even though, so not 32 threads on that socket that normally has 31, even though just like 1 microsecond later, there will be 31 again. So again, the problem is that we take an observation at one point, but that's not really valid for the foreseeable future. So we have some small hacks. I'm not going to go into detail to address these situations. I don't know if these small hacks would actually be acceptable to the Linux kernel developers. The idea is if we remove these situations and the situation improves, if the performance improves, then we can feel some confidence that we have understood things properly. Or if the situation does not improve, we can feel, oh, maybe there's some other things that we need to look into. So we end up with this performance. So here I've made 500 runs to be sure to get the extreme cases. This is the blue line at the top is the original Linux, completely unchanged. And you can see there's kind of a smooth line for a while up to about here, and then it kind of starts veering up to the higher cases. On the other hand, we have the red line at the bottom, which is pinned, which is supposed to be the best case. Note that it also actually increases over time. There's a little upward trend also. And the line that we end up with is this green one in the middle. This one is actually flatter than the others, which is a nice feature, but there seems to be something to understand that I have not looked into. On the left-hand side, in the fastest runs, there is some very fast run, and then most of the runs are not as fast as the fastest run. And we still have a little hook here at the end, which is bigger than the one we get with the pinned, but at least it's close, and so I think we have at least addressed most of the issues. Maybe our mitigations were actually not solving all the problems either. So in conclusion, if you want to understand the behavior of the scheduler, you need to collect all the information about what the scheduler is really doing, but it's a huge amount of information, and so you need some way to actually organize it. And so we have put together several tools. Actually, we've put together a lot more tools than the ones that I've shown here. A lot of tools are very special purpose and not really of interest to anyone beyond understanding a particular application. But these 4 tools we have used quite a bit and have found them to be useful in many different situations. Data graph, so that shows you who's running, where are they running, and for how long, and so on. With that, you can see either the PIDs or you can see the commands. It's different ones are useful at different times. We have running waiting, how many tasks are running, how many tasks are waiting at a particular time. You can also separate that by socket so that you can see in a bit more detail where the overloads are, where they start, how long they last, and so on. Stepper showing in complete detail what's going on every single core and what events are going on. And then the events that can help you see any other kind of events. So we've also used the events tool, for example, for studying locking, when are few texts is taken, when are they released, and so on. So future work, here we have 4 tools. Maybe we could just have one tool that would do everything. And maybe we could also make the tool somehow nicely programmable. because different times you have different requirements. It might be want to stack up a bunch of lines to get a different perspectives and so on. So thank you very much.